I'll be talking about Frientegrity, which is our system for online social networking in the presence of an untrusted centralized service provider. And this is work that I did with my co-authors Aaron Blankstein, Mike Freedman, and Ed Felten while I was still a student at Princeton. So as we all know, current online social networking services are centralized. And this definitely has certain advantages. It's convenient, it's highly available, and it allows users to access their data from all over the place. But it has a well-known downside, which is that now a third party is involved in every user's social interactions, and this gives rise to a myriad of threats. And in particular, the user must trust the provider for confidentiality and integrity of their data. And the threats to confidentiality are well known. They've been in the press. In particular, users' data is vulnerable to theft by attackers, both malicious insiders and outsiders. It's vulnerable to accidental leaks, such as through software bugs in the provider's server code. It's also vulnerable to being repurposed as the providers change their privacy policies in unexpected ways. And finally, there's the ever-present threat of government pressure on these providers to disclose data, potentially without the user's knowledge. However, perhaps less recognized are threats to the integrity of users' data. Now, this could be as simple as a malicious or compromised provider corrupting individual updates, individual messages from the user. But it could take more complex forms. For example, the provider's servers could equivocate. They could show a different view of the system state to different users or different clients. They could show messages in different order, or they could omit certain updates to certain users. And one of the goals of this work is to see whether we could do something about these more complex types of attacks on integrity. Moreover, there has been at least one example of this more complex equivocation in the wild. Sina Weibo, a Chinese microblogging service, kind of like Twitter, used equivocation to actually disguise censorship that it was doing. Basically what happened is when a user who was being censored logged in, it would appear that all of their posts were available for everyone to see. But when other people logged in and viewed their feed, certain ones were missing. In other words, the service showed a different view of the world to different users. Now, the risks to users' data in social networking have gotten a good bit of attention, and there has been quite a lot of prior work in this area. And it's really fallen into two areas. The first approach is the cryptographic approach, which is basically to use various cryptographic primitives to represent the social relationships. However, these typically haven't really addressed the integrity problem, or at most involved digital signatures on individual messages. They haven't addressed this more complex equivocation that I mentioned. The other major approach is the decentralized approach, where the service is provided by a set of federated nodes as opposed to by a centralized service provider. In this case, the federated nodes might be individual users' machines, or they could be a set of service providers from which the user can choose. However, this really doesn't give the user the greatest choice. I mean, this approach has value, but if you run your own server, you have problems with availability and convenience, and many users may not want to do this. And if you have to choose between providers, that might give you more confidence, but in reality, you may not actually know or trust any of the providers that you can choose from any more than you would, or much more than you would, a centralized provider. And so we want to do something different. In particular, we want to allow users to benefit from a centralized provider that supports common social networking features, walls, friends, friends of friends, followers, and so on, but assumes that the centralized provider is untrusted and potentially malicious. In other words, we aim to push the boundaries of the guarantees that are possible in this familiar centralized provider model. And to achieve this, we employ a two-pronged approach. So the first, to ensure confidentiality, we make sure that the provider only observes encrypted data. The data is encrypted under keys known only to authorized users and their client devices. And this, of course, means that we need a way of doing dynamic access control and efficient key distribution. The second prong of our approach is that we want to verify the integrity of all data. And in particular, whenever the server produces output that the clients see, the clients perform a series of integrity checks to see whether not just individual messages have not been corrupted, but they actually check several more complex properties. The most important ones being that it hasn't corrupted individual updates, that the provider hasn't equivocated about the history of updates, and furthermore, that it has enforced access control on writes. So encryption can enforce access control on reads, but you still need to make sure that unauthorized users haven't been able to add values to the history who shouldn't have been able to. In addition, social networking applications have interesting scalability challenges. First of all, much of the data is structured as these long histories, let's say a Twitter feed, for example. It might date back years, but typically users are only interested in the tail, the most recent updates. And so if we want to verify the integrity of this whole history, we would hope that we don't have to verify it every time we check for new updates. So that's number one. The second thing is that typically social networks are comprised of many interconnected objects, walls, comment threads, photos, etc. And we want to be able to shard them across multiple servers to support scalability. Finally, users in these services typically have many friends and even more friends of friends. And so we want to make all access control operations efficient. In particular, we want to make them all run in logarithmic time, including unfriending, which involves changing the key used to encrypt data for your friends and friends of friends. So these goals led us to the following design. Each user profile consists of multiple objects, each comprised of the history of all of the operations that have been performed on it, as well as a single access control list that applies to all of the objects on the profile. And by the way, a profile could be sort of a shared group in addition to an individual user's profile. Now for scalability, clients check for equivocation at the level of individual objects. That is, they check whether the provider is lying about the order of updates to a given object, not to all of the objects in the entire system. However, we also allow the histories of objects to be optionally entangled on an application-specific basis. An example of why you might want this is in a Twitter-like application. If one user retweets another user's post, the service might want to entangle the histories of those two different feed objects. So when Bob, let's say, reads Alice's wall, he of course gets the latest updates to Alice's wall. However, he does not download the entire history, but he gets enough information that he can prove that the server hasn't equivocated about the entire history. In addition, he gets information from Alice's access control list that proves that every operation that he receives as part of Alice's wall was created by an authorized user. And finally, he gets an efficient data structure that allows him to retrieve the necessary decryption keys. So how does this checking for equivocation about the history of modifications to objects actually happen? Well, the way it works is that clients enforce a property called Forkstar Consistency. And what Forkstar Consistency gives you is that if the server is honest, the clients are guaranteed to get a linearizable, that is, a strongly consistent order of operations. But if the server is malicious, then two clients, Alice and Bob, will be able to detect that the server is equivocated if they are able to exchange at most 2 messages. And the way they do this is they compare compact representations of their history by embedding this compact representation in every message they send. Now, if the provider can control when clients are able to communicate, for example, if it mediates all of their communications, it can still fork the clients into disjoint sets that can't see each other's updates. But once it forks them into disjoint sets, it can never unfork them. It can never again allow the clients to see each other's updates. Otherwise, they'll detect the cheating. Furthermore, if the clients can even communicate a little bit out of band, even infrequently, they will detect this misbehavior pretty soon. So this comparison of histories typically has taken the form of comparing hash chains in prior Forkstar consistent systems, such as file systems and key value stores. And computing a hash chain is basically computing a running hash of the history, starting at the beginning and going to the end. But of course, this takes linear time and requires you to download the entire history, not really what we want if we're really only interested in the tail of the history. So Frientegrity does something different. It represents the history as a history tree, which is a data structure introduced for tamper-evident logging a couple of years ago by Crosby and Wallach. A history tree is a kind of growable hash tree in which the operations of the history are in the leaves, and each internal node contains the hash of its children. And so each internal node summarizes its children. And so the root, essentially, the hash of the root, essentially commits to the entire history. So let's say the server signs the root of every revision of this history tree, and let's use the notation C with a subscript of a number to indicate a server-signed commitment up to a particular version of the history. In this case, the history goes up to operation 15, and so we'll make the commitment C15. Now, this data structure has 3 properties that are useful to us. The first is that if we're interested in only the tail, then we can omit the subtrees that we don't need, replacing them with stubs that contain the hash of the omitted subtree. The second useful property is if we want to know whether some arbitrary operation in the middle is consistent with the rest of the history, we only need to retrieve the logarithmic length path from the server down to that operation. Finally, suppose that we have a tree of version 15 and a commitment C15 to it, and then we get a commitment to an earlier version, let's say C8, and we want to know whether these 2 commitments are consistent with each other. Well, then all we need to do is download op8 and then pretend that all of the subsequent operations don't exist and recompute the hashes. And if the computed hash matches the signed hash within C8, we know that those 2 commitments to the history are consistent. So how do we use these properties to actually verify an object, to detect equivocation? Well, suppose that Alice retrieves this object here and wants to verify it, and suppose for now that all users are honest. Every operation is signed by the user that created it and contains the last server commitment that the user who created the operation knew about when they submitted the operation. Now note that this stored commitment may not actually be the one that immediately precedes the operation. This is because operations can be submitted concurrently, and the server can order concurrent operations arbitrarily. So, to do this verification, if Alice thinks that Bob is honest, all she has to do is check whether C11, the stored commitment in that operation, is consistent with the most recent commitment. And then she has to check all of the subsequent operations. And that's all she needs to do. But why is this enough? Well, the reason is because if Alice trusts Bob, she can assume that Bob would not have written op15 unless he had checked all of the operations up to op11. But how did Bob gain that confidence? He didn't check the entire history either. Well, he did the same thing. Op11 was created by Charlie, and it contained the commitment C8. And so Bob only had to check the operations between C8 and C11. And this process can be repeated going all the way back, and so you get something like an inductive proof that basically every piece of the history was checked by a user. And so in this way, clients collaborate to verify the history. But what if not all users are honest? Suppose that Bob is actually evil and is collaborating with a malicious provider. And so that means that the stored commitment C11 could be totally bogus. What can Alice do? Well, one thing Alice can do is look farther back into the history until she finds a point that's been vouched for by more than one user. In this case, op9. And then only verify the subsequent operations from there. And so you can generalize this technique to tolerate up to F malicious users. Now, I should note that F refers to users and not clients. Each user has to be individually invited, let's say as a friend, in order to participate in this object at all. And so malicious users aren't necessarily that easy to come by. You might have to use social engineering or something like that in order to create malicious users. You can't just have a botnet trivially generate a bunch of Sybils. So next, what about access control? We said that it's not enough to just simply check for equivocation about objects' histories. We also need to make sure that the provider is enforcing access control on rights, and we need a way to do efficient key distribution and access control operations in logarithmic time. So in terms of proving access control list enforcement, we represent the access control list, let's say in this case Alice's access control list, as a persistent authenticated dictionary. This is an abstract data type that basically allows for authenticated dictionary lookups. So in our implementation is comprised of a hash tree in which each node corresponds to a user who has access. Now, for clarity, I'm using real names in this example, but in the real system, these are pseudonyms, and I can discuss what benefits that gives you in the questions. And so, like a hash tree, once again, every internal node contains the hash of its children, and so the root summarizes the entire tree. And in this case, it's signed by Alice because this is her access control list. And so suppose that we want the server to be able to prove to Bob that Charlie has write access. And so to do so, the server need only send a pruned version of this tree where the root is signed by Alice and there's a path that goes down to the node containing Charlie. Now, what about efficient key distribution? Well, we can extend this data structure, this same data structure, by turning it into a key graph, by storing a randomly generated symmetric key at each node. Each node stores this randomly generated key encrypted under the public key of the user stored at that node. And furthermore, each internal node contains the key stored at that node encrypted under the keys of its two children. And what this allows is that any user who can decrypt a particular node can follow a path of decryptions up to the root and obtain the root key, which can be used to encrypt data that all of the authorized users can access. So adding a friend in logarithmic time basically just involves adding a new node, picking a new random key, encrypting it under that user's public key. Once again, I want to remind you that these are pseudonyms in the real system. And then just fixing up the encryptions in the internal nodes. And there might be at most a logarithmic number of tree balancing operations here, but you can see how this is very similar to how other balanced trees work. Now, removing a friend is perhaps a little bit more interesting, and unlike many systems, this too can happen in logarithmic time. Suppose we want to remove Charlie, so then we pretty much just need to change all of the keys on the path going to the root from Charlie, and this of course results in changing the root key and changing the key used to share information with all of the friends. So now that I've described this system, clearly we designed it with efficiency in mind, but what about in practice? Do we sacrifice too much for these security guarantees? Well, to test this, we implemented a Java client and server and that simulates basic Facebook features. Basically, it simulates a bunch of user profiles, each of which has a wall and an access control list. We used 2048-bit RSA signatures in our system, and we batched them using a technique also due to Crosby and Wallach called splice signatures. And we performed an experiment on a local area network. And we measured several things. First of all, we wanted to measure the latency of reads and writes to these objects, including all of the necessary verification. We also wanted to measure the latency of access control list changes, throughput, which I won't be discussing here, but it's in the paper, and finally, the effect of tolerating malicious users, as I mentioned a few slides ago. So what about read and write latency? As you can see here, for this collaborative verification, it takes about 9 milliseconds, the median is about 9 milliseconds to do a write, even up to an object with 25,000 operations. And read latency is about 6 milliseconds. And what you notice here is you'd expect behavior to be logarithmic, but actually even up to a history of size 25,000, the constant cost of these 2048-bit RSA signatures, there are a constant number of them, continue to dominate. Now, if you compare this to the hash chain approach that previous systems have used, write performance is about the same, but read performance is much worse. It's basically gets linearly worse as the size of the history increases because you have to verify everything from the beginning. And look at the difference in scale on this graph. For an object with only 2,000 operations in its history, it takes nearly 800 milliseconds to do the verification with a hash chain. Access control lists also display this similar behavior where the constant signature cost dominates the logarithmic number of tree operations. And so here we see that the median latency for adding a user is about 24 milliseconds, and for removing a user it's about 19 milliseconds. You might be wondering why add is a little bit more expensive than remove. The reason is because that requires that public key encryption, encrypting the newly chosen key under that user's public key. Now, another interesting thing to look at is what the cost of tolerating malicious users is. Now, clearly, tolerating more malicious users decreases performance because you have to look farther back in the history until you find a point that's been vouched for by more users. So to quantify this effect, we conducted 2 experiments measuring the read latency of an object containing 5,000 operations as we varied f, the number of malicious users that we tolerate. And so in our first experiment, we chose the writer of each operation, each of those 5,000 operations, uniformly at random from 50 possible writers. And in our second experiment, we chose the writer according to a power law distribution, which better reflects the distribution of messages on, let's say, a message board. And so what we see here is even with 28 malicious clients, and even with the more realistic power law distribution, we still get read latency around 100 milliseconds. Now, you might be wondering about this bend here after 50. Basically, the explanation for that is if we require more than 50 writers before we can stop looking back in the history, and there are only 50 possible writers, we have no choice but to verify the entire history going back to the beginning, and that's why you see that jump there. So overall, I hope that these results show that giving users much stronger confidentiality and integrity guarantees than they have now with centralized providers is indeed practical. Maybe not as fast as Facebook, but within the tens of milliseconds. So to sum things up, we argue that both confidentiality and integrity need protection in an online social networking setting, and it's possible to benefit from a centralized provider while still assuming that that provider is untrusted and potentially malicious. And one of the ways we achieve that in a scalable fashion is by allowing clients to collaborate to defend against equivocation. And we also show how to provide scalable, verifiable access control and key distribution. So thanks a lot for your attention, and I'll be glad to take questions.
Questions?
Hi, Ben Kreuter, University of Virginia. You mentioned using people's public keys when you're adding them as friends.
Right.
I may have missed this, but is there a way to verify their public key so that you, for example, the service provider might be doing a man-in-the-middle attack on everybody?
Right. So we discussed this to a certain extent in the paper. And so the biggest problem is bootstrapping. Basically, once you have one friend or a certain set of friends, then you can basically use their friend network to sort of vouch for the public keys of others. However, because basically their public key will be in the friend's access control list if that key is actually their friend. As for bootstrapping, that's a more difficult problem. I mean, you probably would have to do that out of band through some kind of invitation process.
And have you given any thought to some sort of identity-based encryption for that? Because on a social network, we're really interested in our names, not key fingerprints, etc.
Well, so I think there's a trade-off there. I alluded to the fact that we use pseudonyms here. And basically, the design we assumed here was that these public keys would actually not be attached to names, that they would be a pseudonym generated for the purposes of this service. Now that provides some benefits. It gives you basically it basically gives the provider an unlabeled social graph. Now that is not comprehensive social network anonymity, as I think we all know, because even if the provider has this graph offline, they could potentially do some amount of de-anonymization. But we haven't thought about actually, doing the trade-off the other way and sort of using people's names but doing identity-based encryption.
Thank you.
Thanks for the talk, Yazan Bushmaf, UBC. I see one of the most challenging things is to make this work in reality rather than in simulation, because then you've got your system has to adapt to different APIs, different OSM platforms, and etc. So what's your take on this?
Well, I agree that there are several challenges to implementing it. One of the biggest, as many people have pointed out, is this issue of where the client code comes from. If you're going to rely on the client code to do this verification that I mentioned, you have to have some trust in it. You have this problem where it could come, if the code is all JavaScript coming from the same party, you wonder whether, they could replace the ordinary version of the client code with the spy version that just gives up the plain text or doesn't do the checks right. But this is a problem even outside of JavaScript. I mean, now browsers are updated constantly and automatically, transparently to the user, or apps on mobile devices. And so what we would imagine is, first of all, there would need to be a way to be able to do crypto efficiently on the client side. And second, there would at least need to be a way for others to be able to vouch, other authorities to be able to vouch for the code. So at least there's like a separation of duties here, where the code is vouched for by the client code is vouched for by one party, and and the service provider is someone else.
Yes. So Karthik Bhargavan from India. So you said that in the architecture you envision on the server the data is kept encrypted.
Right.
So you're kind of host proof in a certain sense. But what's the motivation for the service provider to provide this? I suppose Facebook does want to mine your data. Have you looked at like work coming out of Stanford or on homomorphic encryptions, or of Microsoft on cryptographic cloud storage to allow operations to still happen on that data while providing nice guarantees to the user?
Right. So, I mean, we haven't looked at that. Certainly, in terms of the economic model, you know, I don't think that that's solved. I mean, as we heard in the previous question session, there is kind of like this inherent conflict here between the needs of users and the needs of service providers. And, you know, of course, there are attempts at dealing with this, you know, these privacy-preserving advertising models, which do some kind of local mining of data, plus combined with some homomorphic tallying. So that's a possibility. But I don't think we have an answer to that at this point.